A completed 5-story residential building projects total permanence. It sits anchored to the ground, giving the illusion of an immovable, static object. But beneath the luxury facade, this structure is a dynamic system, actively managing hundreds of tons of physical force every second of its existence. The chronological sequence of this construction follows a rigid physical logic, where each stage is a necessary precursor required by structural engineering. Strip away the exterior, and you reveal the skeletal steel and concrete framework hidden beneath. This bare internal system is what actually negotiates the forces at play. To truly understand a modern building, we must deconstruct it and trace its structural sequence from the dirt up. We will analyze the structural engineering physics behind the construction of a modern 5-story mid-rise. Before a single construction material is delivered, the empty plot of land undergoes rigorous evaluation. The required first step is a geotechnical analysis. Engineers test the physical properties of the earth beneath the build site. The results of this analysis dictate the engineering constraints for the entire project sequence. The soil's density and bearing capacity set the strict limits for what can be built on top of it. Every subsequent step in the construction time-lapse is a calculated physical response to gravity and material mechanics based directly on that initial site data. Construction begins with site surveying, heavy soil excavation, and laying the foundation. The required size and depth of a foundation are directly proportional to the soil's bearing capacity. Weaker soil demands a wider, deeper footing. This diagram shows the foundation resolving highly concentrated vertical loads from above. It pushes that downward load across a wider surface area, preventing shear failure. If miscalculated, the building suffers uneven structural settlement, tearing the concrete frame apart. Because of the immense weight it will soon carry, the foundation must be fully cured and stable before upward structural construction begins. Despite its height, a 5-story building is only as stable as the soil's ability to push back against it. Following the foundation work, the construction time-lapse moves to the pouring of the vertical columns and the placement of rebar. This introduces the critical composite material used in modern mid-rises, reinforced cement concrete, or RCC. Looking at this cross-section of a concrete column, we see pure compressive force pushing downward. Concrete excels here with massive compressive strength. However, concrete is highly brittle and weak under tension, easily cracking if bent. To compensate, steel reinforcement is embedded. This steel handles tensile stresses and bending moments from lateral forces, like wind. As the concrete cures tightly around the steel grid, a vital structural synergy takes place, locking the two materials into a single operating system. Neither material could support a 5-story mid-rise independently. The entire construction sequence relies entirely on their composite action. With the vertical columns poured, builders move to floor-by-floor assembly. Every newly poured level must account for dead loads, the static, permanent weight of the heavy concrete floor slab itself. It must also account for live loads, the dynamic, changing weight of future occupants, furniture, and internal fixtures. This 3D view of a floor slab demonstrates how it captures both live and dead loads simultaneously. The weight spreads horizontally across the surface, transferring outward toward the perimeter and funneling into internal structural beams. This horizontal transfer must be completely resolved before the columns for the next floor can be poured. Each assembled floor acts as a massive horizontal net, capturing gravity and safely directing it to the edges of the structure. At the edges of the structure, the physical load shifts direction, moving from the horizontal beams down into the vertical RCC columns. This creates the overarching engineering framework of the building, the continuous load path. The accumulated weight of the 5th floor pushes directly down onto the 4th floor columns. This wireframe traces the load down through each successive story. The accumulated load multiplies exponentially, forcing lower columns to bear drastically more weight. Precision structural joints are an absolute necessity, maintaining an unbroken path of force. The combined forces of all 5 stories finally reach the excavated foundation we saw at the beginning of the project. A modern mid-rise is essentially a highly engineered vertical conduit, designed solely to safely deliver gravity into the earth. In the later stages of the time-lapse, the pace changes. crews construct brick walls, and install electrical and plumbing systems. It is a common misconception that these exterior brick walls are actively holding the building up. In modern RCC construction, brickwork serves purely as architectural infill and environmental partitioning. This split screen clarifies the difference. While historical masonry carried physical weight, the modern structural load path completely ignores the brick walls and plumbing installations. The chronological separation between erecting the concrete frame and adding the brick walls visually proves the critical hierarchy of load-bearing structures versus aesthetic elements. The time-lapse concludes at the final frame, a fully completed building with painted balconies, landscaping, and glass windows. The building is ultimately a composite skeleton, successfully managing immense compressive and tensile forces. The construction timeline serves as a physical manifestation of safe load transfer, reflecting a sequence required by the structural reality of the building. The aesthetic luxury of the final product relies entirely on the hidden, continuous load path beneath it. To appreciate a modern mid-rise, you must look past the plaster and paint to the unbroken physics holding it all together.